Today, me, Jean-Christophe, and Yuri, my coworker, will present to you the different models and different pipelines that we've built for the Richter Predictor competition on modeling earthquake damage during the Nepal catastrophe in 2015. As Erasmus student, I feel like we've really built models that are solid, relatable, and we've also acknowledged all of the things that we did wrong and all of the things that we did good. Over here, of course, we have the different data set, the different packages that we've imported. Most importantly, Keras and the different visualization data sets, packages, sorry. Over here, we've imported our data sets, this is the right. Afterwards, we built functions that were used to calculate the metrics once we did our predictions. And so we can have more insight on if our model and prediction was good or not. Again, these functions were provided to us using the ML metrics package and also provided to us in the course itself. Over here, really briefly, we've merged the initial data set with the building IDs that was provided in the train values CSV. And now Yuri is going to talk more about visualization.
Thank you, Jean-Christophe. So for the data visualization part, we start by looking at the histogram of our variable of interest, which is damage grade. And we firstly see a great unbalancedness among classes. That's why we decided to tackle it in the modeling part by means of a random forest, which is balanced. Balance means we use the class WT hyperparameter in order to set different weights depending on the class. And we can see in this little piece of code that we end up with 3 different weights that we will use later on. And the minority class, which is one as the higher weight, 2, which is the majority class, as the lowest, of course. Okay. Now, proceeding with the data visualization, we see a bivariate distribution of the geo-level ID variables with respect to damage grade, which is done in order to see if there were any visible pattern that we can exploit by means of clustering, for example, in order to do feature engineering. But this is not visible. So we just concluded that with this analysis, was not possible to proceed with feature engineering, and Jean-Christophe is going to explain better how we tackle these variables. Lastly, we see a distribution of numerical variables in order to see if there are any outliers. We didn't find any outliers, but we just found one building which is 1,000 years old, and this is totally fine. I mean, so we decided to keep it, of course.
Perfect. Thank you, Yuri. More precisely here on the encoding, we decided to, of course, encode all of the categorical variables with one hot encoding. More precisely, we've encoded all of the land surface through the legal ownership status that was given to us. But the problem here is that geo-level, all of those IDs were given as numerical data. And so necessarily there's no link between geo-level of 6 and 8 in terms of scale, because they refer to different geographical installments. And so here we hot encoded only geo-level 1, as Yuri said, especially since geo-level 2 and 3 could be encoded with one hot, because it would create a dimension problems for our data set, especially since there's thousands of different numbers for each location, especially for 3 who goes to, I think, 20,000 or something. Over here, we have the function that we use to encode all of the data sets in terms of one hot. Over here, we have all the categorical data that we want to encode. Really briefly, we isolate every column, add it inside of a dictionary, and then we transform the dictionary to a binary matrix and transform all of those matrices, in binary value and assign a name to the columns that we are gonna then add inside of our data set. And then, of course, we remove the initial columns. Over here, we've decided to numerically normalize the the numerical variables. Most importantly, to account for the fact that neural networks are more well built using normalized data. Here we can see all of the data sets and all of the different variables that are encoded.
Okay, so about feature selection, the easiest way to proceed would have been by using Pearson correlation. But since our dataset is really full of categorical variables and binary variables, this was not an optimal choice. And we went for the mutual information. And in this piece of code, we can see how to build a ranking of all the features with respect to damage grade and compute the mutual information. And the dataset is ranked, is sorted, sorry. For the model training, we use just 5,000 observation. This choice is given to the fact that we tried with different number of observations, but we found out that with 5,000 we reached a lot. We reach a lot of sort of cap in the performance. So we just save running time. And this is really important for this function, the training, which is our core function in the training part in the model selection, since we can choose a max number of feature and all the details that I'm not going to explain in the video. And we see just the results. For the decision tree, we see that by increasing the number of features, which are selected from the rank that we just saw, we reached a sort of cap after only 5 features. And then the performance improves, but not that much. And we don't see any kind of overfitting problem. Then for the random forest, we use the balanced random forest as explained before. So we gain explainability from one side because we see that the performance increases over number of features and there is no visible cap after 5, 10, but still at 30, we still can improve the performance. And we will use this model for the final ranking.
Thank you. Here is our last necessary model. We've decided to build a neural network, a deep neural network. So the network is built with 4 layers, so 2 hidden layers and one input and one output. We have 64 units for the initial input, and then 3, of course, because we have 3 types of damage variable, let's say. After that, we briefly compile our data. The problem that we had using the model fit with history is that our data set was really overfitted. And so to account for that, we decided to use early stopping, which is a model that is given to us with KRS. And basically the model stops fitting when there's no more information to be had by going over the data set multiple times. Over here, we have different factors by which it increases. So it increased by 3 times the number it goes over. So this is called epochs. I'm sure you're familiar with it. And that's pretty much it. Over here, we basically use our function, which is train and save model, giving it a train. Here is the train data set. And then we save this model and we give it a name model, and it's a H5 file. Afterwards, we test it, we encode our data set, and then we predict the variables over here. Really, over here, of course, you can see that our predictions are still really overfitted. This is a problem that we acknowledge and that we can see over here, but in our outputs, we can also see a bit of how the neural network is built. So, but mostly this is why we don't use the neural network to do the competition, because it's not that good.
As extra learning procedure, we went for gradient boosting. This choice is given to the fact that for the random forest, we use a balanced model. So we gained explainability that will be useful later, but we wanted a powerful model about predictive power. So we use a pure gradient boosting, and we use it for the submission, achieving a result of around 67%, which is quite good in our opinion. At the end, for the feature relevance by conditional entropy ranking, we developed this little code made by two functions. The first one, the entropy, just compute the entropy given a vector of data. This vector of data will be in our case the vector of prediction, depending on the model. So in the index ranking, we really deploy the conditional entropy. So we train a full model and a lot of model by excluding the I feature, and we fill a data frame that we sort after in order to have the ranking.
Thank you, Yuri. Really, to not go over the time here, we have the model that we use for submitting to the competition, and then we acknowledge some improvements that we could do to the models. First, fixing the overfitting problem with neural network by not only splitting the dataset more well or building the neural network more thoroughly. We could also encode geo level 2 and 3, and finally fetching more types of data by changing the dataset that we use. So thank you very much, and have a good summer. Thank you.
Thank you for the consideration.